to talk about vision in the brain. Don't reach in your pocket. Don't reach in your purse. We have 12 different iterations of the US penny, but only one of them is the actual penny. Which one do you think it is? What do you think? E? J? What else? Anybody, any other guesses? F? It's A. A is the correct penny. Now, how many times have you looked at a penny? A dozen, 100, 1,000, right? And yet, you're not sure which one is the right penny. How could that be? I want to talk today about vision, because we have this impression that our eyes see things, and it goes into our brain, and that's it, right? And it's not. Now, why don't you notice, by the way, do you have to know exactly what a penny looks like in order to use it? You don't. What do you know, how do you tell a penny from anything else? Size, color, right? So you don't need to know all the details. Our brains are incredibly efficient at telling us what to pay attention to or not. So I want to spend some time talking about vision in the brain. First thing I want to say is that your vision is actually imaginary. The things you think are true about your vision are not true at all. So, for instance, when you see something, it arrives in your brain upside down. Everything you're seeing is inverted, and your brain turns it right side up. Everything you're seeing. And there's even these special glasses that you can have people wear that actually then turns it the other way. So when it hits their brain, it's right side up, which means then the brain turns it upside down. So you put these glasses on people, and they walk around, and at first they're kind of disoriented, and then after a while, they're fine. And they can walk, and they can ride a bike, and they can do fine motor skills. And people ask, well, what are you seeing it right side up? Did the brain turn it? No, everything's upside down. Well, how are you able to do all these things? I don't know. They say it just becomes, upside down is just another way to see. So our brain just doesn't change the vision, but it changes everything else so that we're perfectly capable of functioning with things upside down. Here's another way that your vision is imaginary. You actually you're looking around, if you look around right now, you have a whole vision. There's actually a big black hole in your vision. It's where the optic nerve comes out of the eye. There's a hole. But you don't experience the hole because your brain fills it in with what it thinks it should be. In fact, as you scan across the room and it seems like your vision is this smooth, no, you are fixating on one thing, and then your eye jumps to the next thing. Your vision is actually very jumpy, but we're not aware of that either, because the brain is doing all the work. So actually, vision is happening in your brain. And what you see is not exactly the same as what you pay attention to. This is a study from Harvard. Let's take a look. It's about change blindness, when there's changes in your vision and you don't notice. You noticed. And in all kinds of situations, this is true. And if you think it's, oh, because they were looking down, no, it's not. In the research where someone is actually taking a photo of someone, and they're posing, and then someone walks through with a big billboard sign and interrupts them, and they switch the people. And so it's now a different guy standing there. The person taking the picture, looking right at them, still doesn't get it. So we know that we don't see. Now I want to talk a little bit about something called PreAttention. So if I ask you to look for the number 2, find all the number 2s that are in this display of letters and numbers, you can do it. You're looking, you can pick out a few. But if I do that, now it's really obvious where the 2 are. Our brains are wired to pay attention to stuff that changes in certain ways. So color is one of those changes. All the balls are yellow except one is a different color. That's the one we notice. All the lines are one way except one is tilted a little bit different. That's the one we notice. There's actually specific neurons in your brain who pay attention to just that, just a change in orientation. We know that if we change size, that gets PreAttention. If something moves, that gets PreAttention. These are all PreAttention ways. Concave versus convex, which, by the way, is just where the light is. But our eye will see that as being different. So for something to stand out visually, it needs to use one of these PreAttention factors, but only use one. Because look what happens if you use more than one. Up on the top left, we change the color. We notice that. On the top right, we change the shape. We notice that. But on the bottom, we change too many things, and then it doesn't work anymore. Along with PreAttention, we have we have different shapes. So Biederman did this research to show that there are only a handful of shapes that we really recognize, and we use all those shapes, our brains use all those shapes to then identify different objects. And this is an icon, from a software app, and it's for printing, but it has more than just the simple shapes. It has a lot of detail. It has shading. It has the little red and green button. It has a check. When we use all of those details, then those PreAttention features in our brain aren't active. And it actually takes us longer to recognize that icon and what it does. Same with this one, too many details. If we make it simpler, then it'll be easy to recognize. Although we have to ask, why are we using these symbols? Now, some of you look old enough to really know what this is, and others of you don't look old enough. What is this representing? This is the save icon, but what is this? A 3.5-inch floppy disk drive, which was not floppy, okay? Which is named that because of the 8-inch drives that really were floppy. Now, don't raise your hand if you know what that is, because then you're definitely aging yourself here. Why are we even using that, right? So some people are saying we should use a much simpler idea of save, which maybe would help those of us who think of it as a 3.5-inch floppy and those of us who don't. But when we create presentations, when we create products, when we create marketing campaigns or infographics, are we making use of PreAttention? Here we're doing everything, Let's use lots of shapes, let's use lots of colors, and then that PreAttention part of the brain can't kick in. Much better off to back it off, right? Because here we'll notice that blue-green line is changing size, and that's what we're drawn to, because our vision is really calling the shots because of our brain. I want to take a moment and talk about peripheral vision versus central vision. Some of the coolest research on vision is coming out about the differences between central and peripheral vision. So central vision is right here. As I'm looking at you, that's my central vision. And if I'm just going to stare straight at this poor woman that's sitting right in the middle of the auditorium, and if the rest of you, if you move your arms, I can see that. I can see you waving your arms. That's my peripheral vision. Larson and Loschke were very interested in, what's the difference really between peripheral and central vision? So they did this research. They took pictures of rooms, at living rooms, dining rooms, bedrooms, and they either grayed out the periphery and left the central part clear, central vision, or they grayed out the central part and left the periphery clear, peripheral vision. And they wanted to know which way did people more quickly and more accurately recognize the room, when it was central vision or peripheral vision. And the results surprised them, because people more quickly and more accurately recognize the room when the periphery was available and the central vision was blanked out. And they started a whole line of research about, wait, what's going on? And I love their phrase for this. They said, the contributions of central versus peripheral vision to scene gist. The idea that we get the gist of the scene from peripheral vision. You walk into a room, you know you're supposed to go into the auditorium and the meeting room, you're looking at your phone, and you walk in, and you'll suddenly realize, I'm not in the auditorium, I'm in like the men's restroom or something, right? And your peripheral vision will get that right away. Tells you, where are you? And yet we don't appreciate this about peripheral vision. You know, we have so many websites, for instance, that don't do this, that don't use the periphery of the screen. There's nothing on the periphery of the screen. In this case, for instance, our peripheral vision will tell us right away, yes, you are at the restaurant website that you thought you were, because it will see pictures of food. Now, it's really interesting what our peripheral vision actually sees. This is work by Ruth Rosenholz at MIT. She took a picture of the subway map in Boston. And I have a circle there if you're concentrating on the Kendall station in the red line. Here's actually what your peripheral vision sees. You see how blurry that is? So your central vision is clear. Your peripheral vision is really bad. It's really, really blurry because it's not about detail. I had a problem when I put this image in one of my books, and they kept sending it back to me and saying, there's a problem with this image, it's blurry. It's like, no, I want it that way. And every draft of the book, there's a problem with it. It's like, oh, I give up. Our peripheral vision is very blurry, but your peripheral vision calls the shots. The research now tells us that when you're looking over here and you see maybe something over here that's important, your peripheral vision is sending that to your brain and actually gets your gaze and your whole head to move. Your peripheral vision tells your brain, look over here. There's something going on that you need to pay attention to. Another part of vision that I want to talk about is something called the fusiform facial area. And that's going to be on the final. Oh, cool. No, wait. Too much teaching college, right? There's a special part of the brain. It's actually deep in the brain, near the amygdala, in the parts of the brain that deal with social and emotional information. Not the visual cortex, where a lot of our vision happens, but deep in the brain, fusiform facial area. It's a part of the brain that is just sensitive to faces. So it will recognize, is this a face? That's number one. Number two, is it a face of someone I know? In this case, you might recognize this is George Clooney. Do I know this person personally, or is it just someone I know? And then, what is the emotion? What is this person feeling? Which actually, with George Clooney, you can kind of never tell. Right? He's always kind of smirking or something, right? It's like, I don't know what he's feeling. So we know that if we use faces, and anybody who's, creates a website, for instance, or does any kind of print or ad work knows that if you use a face, it's a happy person, it's going to grab our attention. Now, if the face is on profile, it takes our fusiform facial area a moment to a little split second. Oh, I'm not sure that's a face. And then the hair in the way. So it'll take a little longer to recognize that it's a face. Now, we put faces on everything, not just, the fusiform facial area will activate here. It's not a human, but it kind of looks like a face. In fact, a car kind of looks like a face. And that will activate our fusiform facial area. This is a picture from University of Wisconsin, and they had a number of photos for a while where in all the pictures, everyone's looking down, very studious. This was right after they had been named the #1 party school in the nation. And I don't have proof of this, but I think it was in order to do away with that. But I like to take a look at university websites. Like this is University of Minnesota. Apparently, they don't have many people there, but this would not activate the FFA. This would not activate the FFA, fusiform facial area. That would. Arkansas doesn't have people, but they do have squirrels. So that would activate the fusiform facial area. Don't do this, right? So, you know, did you kind of go, ooh, right? That's the fusiform facial area. It's going, it's a face, but there's something wrong. It's creepy, right? So don't do that. All right. Last thing I want to talk about is neuroplasticity. Fancy word. You know, maybe about 10, 15 years ago, and then far back from there, brain scientists, psychologists we thought that the brain was developed when you were young, and then it was pretty set. You know, when you were born, you had certain capabilities. This was our theory. When you're born with the capability to speak, you're born with the capability to see, and then there's some other things that you develop, but by around age 3 or 4, the brain is set. And then all that happens after that is basically you lose brain cells, right? Especially if you drink too much. This is what we always heard, right? Oh, I'm killing my brain cells, right? But about 10, 15 years ago, we began to realize that actually it's not as set and rigid as we think. There's a lot of plasticity. For instance, reading. When you learn you're not born being able to read. Your brain takes other parts of the brain and other resources in order to learn how to read. And I think the most fascinating work that's happening in behavioral science and in perception and in technology is happening with this idea of neuroplasticity. Our brains are much more plastic. So this is a device called the brain port. And this is for people who are blind and have no vision. So they're wearing these glasses. The glasses are a camera, right? So they're wearing a camera, that's a video camera, taking pictures of the world around them. That vision is going, that camera is going into a device they put on their tongue. See that little part that they're putting on their tongue? And so the camera turns the visual impulse into pulses that they feel on their tongue, because they can't see, they're blind. The pulses from their tongue go into their brain, and at first they're just pulses, just like random pulses. But after about 10 or 15 minutes, the brain says, there's something going on here, and it does pattern recognition, and it turns those pulses into a form of vision. Now, it's not a totally clear vision like those of us who have sight would see, but it is a form of vision. And I want to show you a movie here. This is someone who is blind, and he's out with his daughter, and this is just the normal way, right? He's interacting with the world with his stick and with feeling because he can't see. But now he's using the brain port. And that picture you're seeing is pretty much what his brain is seeing. It's turning the pulses of information from the camera on his tongue into vision in his brain. He's able to walk around. He's able to identify objects. He's able to pick up the cup. This one I like. He's now able to play tic-tac-toe. Apparently, he did used to play tic-tac-toe with his daughter, but because she knew he couldn't see, she used to cheat. But now he can see. And now he goes, wait, I have three zeros. Wait, he's going, wait, I won this. She's going, no, I won it. And he's like, no, you didn't win this. So she can't cheat with him anymore. She goes, oh, we both won, I guess. So here are my takeaways for you. Vision is just weird, okay? It is not what we think. And it's not just happening with our eyes, it's happening in our brain. You are actually seeing with your brain. You see what you pay attention to. If you don't pay attention to it, you didn't really see it. Peripheral vision calls the shots, much more important than we think. So if you're doing any kind of design of any product or any situation, think about what's going on in peripheral vision, not just central vision. We orient to faces. Faces are critical. And lastly, our brains are neuroplastic, and I can only guess where we're going to end up going with technology because they are. Thank you.